So good evening. In the last videos, we covered very clearly about the shortest path. Okay, the shortest path, how we can able to calculate from source to all vertices. Okay, so source to all vertices, we implemented Disjeta algorithm in the yesterday video. Now there is some problems in this there is some problem in this algorithm. The problem in this algorithm is nothing but it won't work for negative numbers. If anywhere, if you are having negative numbers, that is negative weights, it won't work. Okay, so that is nothing but a small problem what we have in this Disjeta algorithm. To overcome this particular problem, that means to work with negative values, we have another algorithm is there, which is nothing but Bellman-Ford algorithm. Bellman-Ford algorithm. Sir, the main intention is nothing but, sir, it will find out shortest path from the source vertex, to all vertices. Okay, even if you have negative edges also, negative edges are, I can say, weights. If you have negative edges also, it will work perfectly, sir. But it is a repetitive process, cumulative process. Keep on, you have to calculate. That is the only issue with this. But don't worry, I will take one example for you to demonstrate how it is going to work. Consider I am taking a small graph like this is one vertex and this is another vertex, and here we have one more vertex is there, and here we have one more vertex is there. So here we have one more vertex is there. Like this, I have different vertices are there, and there is a connection between these vertices. Like this we have. Sir, what is the direction here? So it is going to move from this node to this node, and there is a edge from this node to this node, and there is a connection from this node to this node, and there is a connection from this node to this node edge. So there is an edge from this node to this node. Sir, I want to label each and every node values, sir. I can say this is nothing but a 0th node, this is the first node, this is nothing but a second node, this is nothing but a third node, and this is nothing but a fourth node. Coming to the weights, it is having weight that is cast as a 2, and this one is 4, this one is 2. So this one is minus 1 negative value, and this one is nothing but minus 4 negative value, and this one is nothing but 4. Like this we have. Okay, sir, now what is the task here? We have to find out the shortest path, sir. How you can able to find out? Sir, have a look once. First we will see practically how we can able to calculate the path. Sir, initially I am going to take this particular source node to source node. The path is nothing but 0, sir. I mean the cost is nothing but 0, sir. Weight is nothing but 0. Next, remaining all the nodes I'm going to take as infinite. Okay, I'm going to take it as infinite, like how we have done in our previous case. Same structure I'm going to repeat here also. Okay, next, but the only change here is we have to maintain, okay, these things in the form of table. We have to repeat. Sir, how many edges are there in our things? Sir, we have almost four, 1 2 3 4 5 vertices are there. That means you have to run loop for 4 minus 1. 4 minus 1, that is nothing but 4 times. Cumulatively you have to calculate the weights, then only you people are going to get the full-fledged weight, sir. So for this, I am going to represent a diagram like this is nothing but 0th node. This is nothing but the first node, second node, so third node, fourth node. Like this we have. So by default, what are the weights? Sir, first node weight is nothing but initially 0. So remaining all nodes weight is nothing but infinite, sir. Remaining all nodes weight is nothing but infinite. Sir, you have to repeat this for 0 times. Sorry, for how many times? 4 times you have to repeat. first time, second time, third time, fourth time. Keep on, you have to repeat so that you will get the minimum value. Okay, so that you are going to get a minimum value. Now my requirement is, sir, I want to do this operation with the help of a small things, sir. Like, sir, first thing, I will start from the source vertex. Sir, to meet from 0 to 1, this edge I am taking now. To meet to 0 to 1, sir, what is the cost? What is the actual weight here? 0. 0 plus 2. 2. Is it less than infinite? Yes. Then update with this as a 2. What is another edge? 0 to 4. Sir, 0 to 2, the weight is nothing but 4. 0 plus 4 will become 4. Is it less than infinite? Yes. Update with 4. Listen my words carefully. Next, we have to take, sir, 2 adjacent node, 1 adjacent node. Sir, 1, 2, any other edge is there? Sir, here we have to take 0 to 1 after completion of this 0 to 2. Sir, 0 to 1, is there any other edge? Yes, we have, but first we will visit 2. This edge I will take. This edge I will take. Okay, sir, to move from, no, better to go for this format. We will take 1 to 2. Sir, 1 weight is nothing but 2. But here, what is the edge cost from 1 to 2? Minus 4. 2 minus 4 is nothing but minus 2. Is it minus 2 is less than 4? Yes. Then update with minus 2. But listen my words, somewhat confusion will be there for you people. Listen. Sir, to move from 0 to 2, I have to spend 4 rupees. I have to spend 4 rupees. Sir, to move from 0 to 2, I have another path is there where I have to spend 4 rupees. I am going to get 4 rupees. That means the total cost what we have here is minus 2. That means I am spending 2 rupees. For me, I am getting minus 4. That means what? So 2 to get cancelled, minus 2 is in my side. So I have to spend 4 rupees. My balance is 4 rupees, but here I am getting minus 2. That means which is the smallest, sir? This one. So this is nothing but the shortest path. Like this, we have to consider when you are getting negative numbers. Sir, similarly, what is the next step? Sir, to move from 3 to 4, to move from 2 to 3. Sir, what is the cost? Minus 2. Minus 2 plus 2 will become 0. Is it less than infinite? Yes. Next, sir, next edge 3 to 4. Sir, what is the cost here? 4. 0 plus 4. 4. Is it less than infinite? Yes. Now observe carefully. Sir, I am taking 4 to 1. 4 to 1. Sir, this edge also we have to cover. Sir, what is the weight? 4. 4 minus 1. Sir, 3. We have to update with 3 or not? 1 second, 1 second. To move from 4 to 1, we required minus 1, 4 minus 1, 3. Yeah, correct. Sir, 4 minus 1, which is nothing but 3. Sir, is it less than 2? No, that's why no need to update. Sir, what is the final result in the first iteration? To move from 0 to 0, 0. To move from 0 to 1, how much cost is required to? Sir, to move from 0 to 2, minus 2. To move from 0 to 3, sir, 0. Correct. Sir, to move from 0 to 4, sir, what is the cost required for? Like this we have. Sir, same process again you have to repeat. So again you have to repeat starting from 0. Sir, to move from 0 to move from 0 to 2, because with these updates there may be a chance of affecting these edges, but in this example there is no change. Even if you calculate, we are getting 0 plus 4. Sir, 4 is less than 2, again we will get 4. Okay, by taking infinite again you have to repeat it. Sir, same values only you will get. So when you are going to get changes means if there are more number of edges, and with this if there is a change in the path, so that's why there will be a change. But in this example, there is no change, sir. Even if you calculate for 3 times, you will get the same values. When the change will be there, when you have more number of edges, and this diagram is somewhat different means we will get. That example I will show you. Don't worry at all. Okay, I will give that example. Don't worry. Like this, we can calculate. Sir, this process is nothing but what we can call, sir, Bellman-Ford algorithm. Bellman-Ford algorithm. I think you people got theoretical clarity about this algorithm, sir. Once if you are okay with this, I will implement this program. Can you please confirm? Is it clear up to this? Theory part. Right. Now, let's go for implementation. Let's go for implementation. Sir, how to implement? Of course, we need edge. Everything is required. I think here we are not going to use any priority queue. Okay. So I'm removing this disjotter algorithm. In this place, I want to take same algorithm, or we will change the graph. I'm taking static void. So Bellman. Okay. Bellman Ford algorithm. So which is going to take a graph G, and integer I'm going to take a source vertex. Integer, the distance what we are going to get is nothing but G dot V. How many vertices are there? Those many times. So I'm going to initialize that distance vector. I is equal to 0, I less than, so distance dot length I plus plus. So if the value of I is not equal to source, your I value is not equal to source, then I am going to take a distance of I is equal to, we have to assign integer data max underscore value. You have to assign maximum value for this. Next, for integer I is equal to 0, I less than number of vertices minus 1. Okay, I plus plus. I told very clearly we have to run 5 times, sorry, 4 times if number of vertices is 5. So that's why I'm taking this loop. And in this, I'm going to take one more loop. J is equal to 0, j less than. For all vertices, we have to calculate the distance for this purpose. And for each edge E, so present in this temp. Sir, meanwhile, you have to calculate a temp or not. Yes, temp is nothing but all the list of adjacent vertices which are for this list. So I'm taking linked list. It is going to hold edge. So temp is equal to graph dot adjacency list dot get off. So we have to take j. For j, that is when j is equal to 0, which are adjacent nodes for j. So for everything, you have to calculate u value. UV is nothing but E dot source. And we have to calculate V value. V is nothing but sir E dot destination. And we have to calculate weight, which is nothing but E dot cost. Like I'm taking. After this, formula is as usual. So distance of, okay, distance of U is not equal to integer dot max value. Okay, integer dot max value, and at the same time, so previous formula, that is this condition is for negative numbers. Okay, so distance of U plus weight is less than, so distance of V. If it is the situation, then what we have to do, I'm going to update a distance of V will become, so distance of U plus weight. That's all. That's all. Sir, now we have to print that final distance vector list, sir. For I is equal to 0, I less than distance array dot length I plus plus. Every updated distance it will print. SOP of, I am going to take a distance of I followed by space. Now what it is going to display? It will display all the distances from 0 to the vector, I mean the edges, whatever we have, vertices, whatever we have. But we need to change the graph. So the number of vertices is 5. So 0, 1, 2, 0, 2, 4. So 1, 2, minus 4. 0 to 1, 2, 0 to 2, 4. So 0 to 2, 1 to 2, minus 4. Next, we have to take 2 to 3. 2 to 3, it is nothing but 2. So 2 to 3, it is nothing but 2. So next we have 3 to 4, it is nothing but 4. So 3 to 4, which is nothing but 4. Next 4 to 1, minus 1. So 4 to 1, which is nothing but minus 1. Like this I am taking. I will print the graph. At the same time, I want to call this Bellman-Ford algorithm. Now we will see really is it going to print that path or not. Sir, 0 minus 2. Sir, 0 minus 2. Sorry, 0 2 2 0 4. This is nothing but whatever weights that you are going to get. That is nothing but the final cost what we have, sir. So I think how to work this Bellman-Ford algorithm for calculating So shortest path from source to all vertices, you people got very clear clarity, sir. Can you please confirm any doubts up to this? Everyone please respond. Any doubts up to this, please confirm. Clear? Right. Sir, next I'm going for one more application of graph, which is nothing but, sir, minimum, okay, minimum cost spanning tree, minimum cost spanning tree, MST. Sir, what is mean by minimum cost spanning tree? Very simple. So a minimum, okay, a minimum cost spanning tree, okay, or minimum weight spanning tree, any word you can use. So minimum cost or minimum weight spanning tree, any word you can use. So in short form it is called as MST. Is a subset of the edges, the subset of edges of a connected graph. Okay, connected edge weighted undirected graph. Okay, so that connects all the vertices. It has to connect all the vertices together. Okay, together. Okay, so without any cycle, sir, it should not form any cycle, and minimum cost should be there. Minimum cost should be there. Like this, if it is framing any tree, then you have to consider that tree as minimum cost spanning tree. Sir, I will take one example so that you can understand well what is mean by that minimum cost spanning tree. Consider I am taking one simple diagram, sir. It is easy only. Don't feel it is a difficult task. It is easy one. Consider I have one node is there called A, and we have another node is there called B, another node is there called C. Sir, another node is there called D. Okay, sorry, D. And then we have another node is there called E, and here another node is there called F, and another node is there called G. Like this we have. So this is nothing but I am taking node A, and this one is node B, and this one is node C, and this one is node D, this one is node E. So this one is node F, this one is nothing but node G. Like this we have. Now there is a connection. Okay, now so there is a connection from A to B. There is a connection from A to B, and there is a connection from B to C, and there is a connection from A to D, and there is a connection from P to D, and there is a connection from P to E, and there is a connection from C to E. Now there is a connection from, sir, B to E. Next, sorry, D to E. Then there is a connection from these two, and there is a connection from these two. Then there is a connection from these two. Then there is a connection from these two. Like we have a big graph is there. Of course, here we have weights are there for this. Its weight is 7, so its weight is 8, its weight is nothing but 5, so its weight is nothing but 7, and its weight is nothing but 5, and its weight is nothing but 9, and this weight is nothing but 15, so this weight is nothing but 6, so this weight is nothing but 11, this weight is nothing but 8, this weight is nothing but 9. Like this we have. Sir, what is our task here is, listen my words carefully, sir. We have to construct a tree. We have to construct a tree that is called as MS tree. Means what? Minimum cost spanning tree. So that every vertex should be there, sir. Every vertex should be there. Every vertex. Whatever vertices we have, same vertices should be there. Sir, what vertices we have? This is nothing but A. This is nothing but B. This is nothing but C. So this is nothing but E. This is nothing but D. And this is nothing but F. This is nothing but G. Like this, we have all vertices should be there. So A, and then sir C, and then so B, and then D, and then E, and then F, and then G. Like this we have. But sir, what about connections? You have to check whether your connection is going to frame any cycle or not. Sir, from A to B, A to B. we have to add. Sir, add this edge, no problem, no problem. Sir, we can add A to D. There is a connection. Sir, if you add B to D, is it going to form a cycle or not? Yes. Then don't take this. Then B to C, you have to connect every vertex. Then, sir, can we connect them? Okay, then can we connect them? This this C and D? Yes. Okay, then can we connect this one? No, we should not connect this one. But sir, have a look once. Sir, its weight is 8, its weight is 7, its weight is 5. Sir, I think better we can connect like this, right? Okay, you can connect B to E and then you can connect C to E, because this cost is very high, right? 8. That's why I'm not taking. And even here, this cost and this cost are very less when compared with this cost. That's why we included this. Like this we have. Sir, is it framing any cycles? No. Then, sir, what about D to F? Can we connect these two? No, it will frame a cycle. Can I connect D to F? Yes, only one possibility. No problem, you can take. Sir, can I connect F to E? No, because cycle it is going to form. Already connection is there. Okay. Next. Sir, can I connect E to G? What is its cost? 9. Yes, we can connect. Sir, otherwise we can connect F to G also, no problem. But it is going to take how much weight? 11. But if you connect these two, how much weight we are going to get? 9. Sir, minimum cost we will get, right? This is nothing but all vertices which are there in the tree is available at the same time. At the same time, the edges are connected with all vertices, sir, and it is not going to frame any cycle. Such type of graph, I mean such type of tree, subset tree, is called as minimum cost spanning tree. For developing this minimum cost spanning tree, we have two algorithms are there: Prim's algorithm and Kruskal's algorithm. These two algorithms I am going to demonstrate now in today's session, sir. Can you please confirm, is this concept of calculating minimum cost spanning tree, is it clear for you people, sir? I request everyone to please confirm. Is the concept is clear for you people? Is the concept is clear for you people? Please confirm. Right. Right. Sir, now I want to talk about, sir, next algorithm. I want to talk about Prim's algorithm. But anyway, I need to see in detail about this Prim's algorithm, sir. I need to go for in detail about this Prim's algorithm, how it is going to work. First, I will explain step by step process, sir. First, I will explain step by step process. Sir, how it is going to work. Listen carefully. I will take some other diagram because I need to explain with in detail. So I will take a small example. So consider I have a node 0 is there. Okay. So a node 1 is there and a node 2 is there and then a node 3 is there. Like I have three nodes are there. So this one is nothing but 0. So this one is nothing but 1. This one is nothing but 2 and this one is nothing but 3. Sir, there is a connection between all these nodes: 0 to 1, 0 to 2 and 2 to 3 and then 1 to 3. Like we have connection and here also we have connection. Coming to the cost, sir, its a cost is 10, its a cost is 15 and its a cost is 50 and its a cost is 40 and this one cost is nothing but 30. Like this we have. Now what is my requirement here is, sir, we have to find out minimum cost spanning tree. Sir, there are two possibilities are there for this tree. There are two possibilities are there. Sir, what are those possibilities? first possibility, okay, first possibility, observe carefully. Two kinds of minimum, I mean, spanning trees are possible. Two types of spanning trees are possible. In that you have to select minimum cost. In that you have to select minimum cost. Sir, what is the first one is nothing but consider this node is 0, this is 1, this is 2, and this is 3. And here also it is 0. So it is 1, it is 2, and it is 3. Like this we have. Sir, what is the first possibility? I will connect 0 with 1 because it is having minimum edge. Sir, next minimum edge is what? 15. Okay. Sir, next term, this one 30. So I don't want to connect. Okay, I will leave as it is. Sir, can I take 1 to 3? Is it going to frame any cycle? No, no. Yes, it is one possibility. Then, sir, 0 to 1. So 0 to 2. Can I connect 0 to 3? Because if you are not connecting these two, it won't form any cycle. So this is also minimum spanning tree. This is also minimum spanning tree. Two minimum spanning trees are there. Sir, what about weight? Its weight is 10. Its weight is 15. Sir, its weight is nothing but 40. Sir, its weight is nothing but 10. Its weight is nothing but 30. Sir, its weight is nothing but 15. Sir, what is the total cost of this particular spanning tree? Sir, 10 plus 40, 50. 65 is nothing but a total cost. Sir, for this spanning tree, what is the total cost? Sir, 10 plus 30, 40, so 55. Now, in these two, which is minimum cost spanning tree? Sir, minimum cost spanning tree is not this one, because we are getting minimum cost. This is nothing but the concept what we have. By keeping these two in mind, what is the first one? It should not form any cycle. What is the second constraint? All vertices connection should be there, and whatever possibilities are there, with that you have to get minimum cost. By using this, we have to find out minimum cost spanning tree. Can you please confirm everyone? Is this concept is clear for you people? Same example only, just I have taken one another example for understanding purpose. Right. Sir, for this algorithm also, I need to go for pair class, all these things. So that means this program should be as it is available. Okay. So which things are required? Edge class is required, and even this pair class is also required. But in this pair integer, instead of path, I am going to take cost, because based on cost only we have to do modifications. Okay. So pair, which is going to take cost value. Okay. So this dot cost will become cost value whatever you are giving, and compare to, sir, with which attribute it is going to compare? Not with path, it will compare with cost. Okay. Then we have to write a prims algorithm for calculating this. Okay. Now I am writing static void. So prims. Okay. So prims algorithm for calculating minimum cost spanning tree. Minimum cost spanning tree, which is going to take a graph. Sir, now I will take Boolean array as usual, visited is equal to, so new Boolean of, okay. So new Boolean of, it is going to take G dot B. Similarly, I am taking one priority queue. So priority queue PQ is equal to, so I am taking new priority queue of new priority queue of, sir, which is going to hold like this, but here this priority queue is going to take pair, it is going to add with pairs. Next, first we have to add the first one, add of, so new pair I am creating, where, sir, the first vertex is nothing but 0, its minimum cost is nothing but 0, like this. Now we have to prepare final cost, because that is our main calculation, right? Final cost is 0, and we have to fetch one by one value from the priority queue until your priority queue is not empty. Until your priority queue is not empty, and I will get the pair current pair is equal to pq dot remove. So that first pair which is there in the queue, it is going to be removed, and not of visited of that current dot n. Current dot n or v. In that current priority queue, we have taken n. Okay. So that n is not visited means then you have to perform these operations. What is that? So make that particular vertex as visited. That is the first operation. Then update the final cost. Final cost will become, so final cost plus that current node cost I am going to add. Next, and after that, try to find out its adjacent list. So temp is equal to, sir, graph dot adjacent list dot get of that current dot n. Sir, which are adjacent nodes? All these nodes we are going to get. Now what we are doing, for each edge key value present in the temp, take one by one edge and try to add it into priority queue. Sir, have you observed in the priority queue, whenever you are adding the pair with the destination comma cost, it is going to take always minimum cost. Okay. So next time while fetching, it will take always minimum cost. That's all. Our loop will perfectly work. Then at last, what is your requirement? You have to print final cost, sir, which will become that minimum cost spanning tree. This is nothing but the concept what we have. Sir, after this, just we have to call graph dot, so prims m minimum cost spanning tree of this graph. Sir, I will take this graph as, so which graph I can take? For example, I will take this graph for easy understanding purpose. How many nodes are there? How many vertices are there? 4 vertices. Sir, what is the connection? Let me take 0 to 1 is there with the cost 10. 0 to 1 is there with the cost 10. Next term, sir, 0 to 2 is there with the cost 15. 0 to 2 is there with the cost 15. Then 0 to 3 is there with the cost 30. Okay. So then 1 to 3 is there with the cost 40. So then 2 to 3 is there with the cost 50. Like this we have. Now we will see what is the minimum cost spanning tree that we are going to get for this. Have you observed? 55 is nothing but the minimum cost. Sir, among these two, we are getting this one or not? Yes. Why we are getting this one? Because this cost is very less. That's why it is not added. Suppose if you take more value for this, and we will see whether we are getting 65 or not. In the place of 30, let me take 50. In the place of 30, let me take 50. Now see what will happen. Is there any change or not? Sir, have you observed? We are getting 65 as the minimum. Okay. Like this, if you change the values, definitely that impact will be there. This is the way how you can calculate minimum cost spanning tree by using which algorithm, sir? Prim's algorithm. Can you please confirm everyone, is the concept of calculating this minimum cost spanning tree, is it clear for you people, guys? Please confirm everyone. Clear? Right, sir. So the next one, what we have here is, sir, this particular algorithm, even you can calculate by using, sir, Kruskal's algorithm. Kruskal's algorithm is also there. By using that algorithm also, we can calculate minimum cost spanning tree. Okay. Sir, how to do that in Kruskal's algorithm? Very simple, sir. If you take this diagram, okay, if you take this diagram, 1 second. If you take this diagram, sir, how you can able to calculate by using Kruskals, I will explain. Sir, in the place of Kruskals algorithm, I have to change the code also. Listen carefully. Sir, how it is going to be taken? Sir, first step. Okay, first step. Sir, of course, we have edges will be there. Sorry, vertices will be there as it is. Vertices will be there as it is. So with the names, this is nothing but a 0 vertex. This is nothing but a 1. This is nothing but a 2. This is nothing but a 3. Sir, we have edges are there, right? Based on edges, it is going to work. Sir, among these things, which is the minimum edge 0 to 1? First, it will add that one. Based on edges, it is going to do sorting. Sir, what is the first edge? This will be considered. Excellent. Now, what is the second edge? 10 completed. Sir, based on sorting, which is next one? 15. Sir, it will connect this one, 15. Okay, 15. Sir, next, which is the minimum edge next one? Sir, 30. 30. Take this, like this we are going to get 30. Sir, next, which edge it is going to come? 40. Sir, is it going to frame any cycle? Yes, don't include. Sir, is it going to frame any cycle? No. Sorry, yes, don't include that. That's all. Sir, have you observed? Same answer only we got, right? Sir, even if you take this diagram also, already we calculated minimum cost spanning tree by using, sir, which algorithm I explained here? By using Prim's algorithm, we have seen this. Now I will apply Kruskal's algorithm for this. Sir, what nodes we have? We have A node is there, and we have B node is there, and we have C node is there. So we have D node is there, we have E node is there, we have F is there, we have G is there. Let us label these nodes. This one will become A, so this one will become B, this one will become C, this one will become D, so this one will become E, this one will become F, this one will become G. Like this we have. Now what is our task? We have to add the edges which are having minimum cost. Sir, among these three, which is the minimum? I think 5, right? Sir, any other nodes are there other than this 5? No. Sir, we will add this one. Yes, make the connection between A to D. Sir, its weight is nothing but 5. Excellent. Now, what is the next value? Again, we have another 5. Sir, is it going to frame any cycle? No. Then add this, and this cost is nothing but 5. These two will be added. Next. Sir, next one which we have to consider among these, is there any 6? Yes. D to F. Try to make a connection. D to F. Sir, its weight is nothing but 6. Like this we have to take. Sir, what is the next one after 6? Is there any 7? Yes. We have A to B is there. Can we connect? Is it going to frame any cycle? No. Happily you can connect. Then, sir, B to E is also there. Okay, B to E is also there with value 7. B to E is also there with value 7. Try to add. B to E is there. So with value 7, try to add. Excellent. Now, what is our next task? Sir, after 7, we are going to get 8. B to C is there. Can I add B to C? No, because it is going to frame a cycle. Okay, don't add. Next, we have another 8. Sir, which is that? E to F. Can I connect E to F? No, because if you connect E to F, is it going to frame a cycle or not? Yes. Sir, next, what is the next value? 9. Sir, E to G. Can I connect E to G? Yes, no problem. It is not going to frame any cycle. Sir, what is its cost? Its cost is nothing but 9, sir. Next. Sir, what is the next value? Here we got again 9. D to B. Can I connect D to B? No, because it is going to frame a cycle. Sir, what is the next value after this? Sir, we have 11. Can I connect F to G? No, if you connect, it is going to frame a cycle. So don't include that. Sir, can I take 15, which is nothing but D to E? No. Sir, immediately we are going to get a cycle. Sir, I think that's all right. Yes. This is nothing but minimum cost spanning tree by using Kruskal's algorithm. In Prim's algorithm, what we are doing? We are looking for the connections. While connecting, we are looking for adjacent nodes and with minimum cost. Suppose for A, which are adjacent D and then B. In this, what is the minimum cost? 5. Let me add. So next A to B, is it going to frame any cycle? No, then add. Like that it is going to work. But in the case of Kruskal's algorithm, what it is doing? It is going to sort all the edges according to their cost. One by one we are going to add without framing any cycle. Sir, can you please confirm, is the outline concept of this Kruskal's algorithm, Kruskal's algorithm, is it clear for you people? Sir, I request everyone to please respond because majority of the students are not responding properly. I request everyone to please confirm. Yeah. Sir, for this Kruskals algorithm, already I have code is there. I will execute that code, sir. Already I have code is there. I will execute that code. Have a look once. Yes. Sir, I am implementing Edge class. So Edge class itself is implementing comparable interface. Means what? In the edges we have to, because our main intention towards Kruskal's algorithm is nothing but to sort the data based on edges. That's why I'm using comparable interface. So source, destination, cost will be there. I am implementing compare to method by comparing these two cost, current edge cost and then the edge which you have passed. Those two cost I'm going to add. Now I will create a graph with some edges. Sir, in this case, you can see the graph is nothing but something like we have, sorry, we have 0 vertex is there. So for that 0 to 1 cost is nothing but a 10. So 0 to 2 is there. Sir, cost is nothing but uh, 0 to 2 is there. So cost is nothing but 15. So 0 to 3 is there. So cost is nothing but 30. So 1 to 3 is there. Cost is nothing but 40. So 2 to 3 is there. Cost is nothing but 50. Like this we have. I added all the edges here itself. Next, the number of nodes are nothing but 4. And I'm going to create, sir, parent nodes and then rank. Okay, anyway, I will discuss about this in our priority queues. Don't worry at all. Sir, here the main operation here is nothing but a Kruskals. Sir, first I am going to initialize all its parent. Whenever we are calling init method, all these parent nodes will be initialized with their nodes itself. For 0, who is the parent? 0. For 1, who is the parent? 1. Like that it is going to initialize. So next, I'm going to sort the edges. So based on ascending order. Then minimum cost I'm going to calculate and the count will be initially 0. Sir, for n minus 1 edges, I'm going to do. I am going to get the edges one by one and I will call parent of A, parent of B, source and then destination. If these two are not the same, then I'm going to combine. By combining this, it is going to find out the shortest distance and it will combine. Okay, that part I will take it in priority queues, sir. Okay. Sir, now we are going to find out this pair is eligible or not. So it is going to search for the appropriate edge and it will add. Once if the edge is added, that cost I am calculating to minimum cost and count plus plus. So how many times it is going to work until your edges is less than the number of vertices minus 1. So finally we have to print minimum cost. In this example already we have seen what is the minimum cost that we are going to get. So 30 plus 10, 40. So 40, 55 we have to get. Now let us execute this code and check how it is going to work. Is it going to return 45 or not? We will see. Sorry, 55. Yes, this is nothing but minimum, sorry, what you can call Kruskal's algorithm, which we have to use for calculating minimum cost spanning tree. Okay, among this tree, which nodes, which edges, if you connect, so that it should not form any cycle, it has to form a tree, and based on that, what value we are getting. I think you people got some clarity, sir. In these two new concepts you got, one is nothing but how you are going to combine these union operation. Next and after that, priority queues. Okay, so that value that part we are going to discuss in our next upcoming priority queues concept. Can you please confirm, is the concept is clear for you people? Everyone please confirm. Right, sir. Right. So with this, these graph concepts got completed. Still some other algorithms are there, but I'm not concentrating fully on this. Next, we will talk about the priority queues in the tomorrow's session. Sir, tomorrow class is there. I'm going to discuss about the priority queues and I will try to finish these priority queues on tomorrow, sir. Okay. Better I will give dates also so that we can estimate, we can give the estimation date for course completion. Okay. Yes. So tomorrow So 2/4/2023, as usual, 7 p.m. we will have class. I will complete priority queues. After completion of priority queues, these time and space complexities I will cover on third. Okay. And these greedy algorithms and dynamic programming. These two I will cover on fourth, sir. Okay. So next, this divide and conquer. Divide and conquer. Of course, it is a small part. I will talk on this fifth. So next and after that, these red black trees and AVL trees. So sixth and seventh, yeah, I will cover, sir. Maximum by 7th we will wind up this course. Okay, by 7th we will wind up this course. Okay, so tomorrow class is there. I am going to finish priority queues tomorrow. Okay, in that only heap sort will be there. That part we will discuss tomorrow. Okay, right, sir. Thank you. I will upload these running notes. Actually, this running notes is not updated. Today I will upload these running notes for every batch. Okay, right, sir. So thank you. We will meet for the continuation tomorrow as usual at 7 o'clock. Thank you, guys. Videos access will be there for 7 months, madam. Right. Thank you.